So, very good afternoon to all. Today we will go for a study about LVDT characteristics. So that now this is the practical demonstration about the LVDT kit. This is your LVDT kit. Before that, going in deep, we just go for a block diagram representation of a displacement linear variable differential transducer, so that you can see this is the sensor is sense the physical parameters. So for in our case, from the sensor is our LVDT, a linear variable differential transducer. So from the LVDT we can measure the displacement. Okay, so the LVDT is give if you provide a physical change in a displacement, it gives a voltage or current signal to your signal conditioning devices. Because of the signal over here from the sensor is very low voltage, we need to amplify, we need to filter out. So there is a signal conditioning devices which can capable to reduce unwanted signal, as well as amplify or scaling the input signal to your microcontroller. Another one is microcontroller that can be have a ability to take a decision, to have a numerical or arithmetic capability, and give a command to various output devices. So first we sense the input detection, physical change in a displacement, then we scale up the signal in millivolt to voltage, and the microcontroller is a measure the input ADC signal, okay, analog signal, through the signal conditioning devices, and trigger or give a signal to a display unit. So here we have a LCD, so we get a display about the what is the distance and what is the voltage over here from the LVDT. Similarly, some LEDs or some alarm signal are there, some visual alarm or as well as audio alarm is there. So now here you come here. So now this is the tube is here. So inside this tube we have a 3 winding. So primary winding, similarly the block diagram is represented here. So primary winding, it is energized by a fixed AC source with a heavy frequency, a certain fixed frequency. Similarly, in secondary winding we have as ES1 and ES2, two windings. Okay, so both are connected in this tube as such as that give a signal if you change a armature motion. Okay, inside armature, if you provide a armature displacement, then we get a output output change in voltage approx secondary of both secondary. So now this is the LVDT tube, and this is our screw gauge to calibrate our LVDT with screw gauge. Okay, so by moving this armature, we can move the armature from that knob. Okay, so now you see here what is the rating of this tube. It can be measure the range of displacement from 0 to 20 mm. So we can move either from 10 mm to 0 or 10 to 20. So our center point is 10 mm. Okay, now come here. This yellow waveform is your input waveform for a primary winding of LVDT. So you see that this is a sinusoidal waveform having a frequency of very high frequency, is a 3.8 kilohertz frequency. Similarly, is a blue one and purple one are both are ES1 and ES2. Okay, so if it is centered, if the armature is a center of both winding, then we get a equivalent RMS voltage to CH2 channel and 3 channel. Okay, and the display unit is here, so it can sense, it can visualize the what is the distance and what is the output voltage across the ES1 minus ES2. Okay, similarly this is your LVDT is connected to that RS232 port, so we get a signal from your sensor is here. Again, this is your signal conditioning or amplifier. So op-amp is there, and op-amp is amplify the millivolt into in voltage, so that we get a input voltage to our microcontroller. So this is your PIC microcontroller is here, and we get a alarm signal like buzzer is here, like if we move in a left side, then it is this LEDs move, this is glow. Otherwise, if we move armature in a right side, then this LEDs glow. Similarly, the display and the display unit show you about distance, what is the distance of armature, and similarly what is the voltage appear across the LVDTs. Okay, so now similarly, if you see both the ES1 and ES2 waveforms, you see here.
मास्क लगा रखा है.
So if you see, this is your primary winding waveform, input waveform, and you get a ES1 waveform and ES2 waveform. Okay, so ES1 and ES2 both are in a same. Okay, but here if you connect it, pause. So you see here, this is your primary input voltage to a primary coil of LVDT. Blue one is your ES1 voltage, and purple is your ES2 induced output voltage through a secondary coil. Okay, both waveforms are a 180-degree phase shifted. So when it is peak, then it is down. When it is down, then it is have a peak. Okay, so both have a 180-degree phase shifted. Now I will go for a readings, okay, to observation of the kit. So first we need to set it to a 0. So I just set to 10 mm. So now our screw gauge is set at a 10 mm. Okay, so suddenly the output is here, is a buzzer is horn that we set the LVDT at a center point. Okay, so that's why we get a here is a 0 mm displacement. Similarly, output voltage, this is residual voltage of a 20 or 19 millivolt. Okay, so now if I move a LVDT in a left side, armature in left side, then suddenly we can see that if we move a 1 mm, then voltage is also positive and direction is also positive. Similarly, if you move armature more and more in left side, then we get a distance or displacement more and more. Similarly, voltage is also in positive. Okay, so we can move a armature of maximum 10 mm. So I just set it to a 10 mm and see that. So we get a 10 mm here. So here you can see that at 10 mm we just go with the screw gauge is a 20 mm. So we can move a armature to its maximum limit. Okay, similarly for that's why we get a 10 mm and distance is also positive 1. Okay, so we if you draw a waveforms, then we centralize the armature and move in left side in armature, then voltage is increase, but voltage is positive. Okay, and it is increase. Now you see here, if you move a distance from 10 mm to 20, we get a waveform like that. Okay, more if you increase the armature beyond the 20 mm, our core is saturated, so we get a maximum output here is a 1 volt. Okay, so this waveform is appear in our graph. Similarly, if I move the armature in the right side, then see that. Similarly, if you see another one explanation is here. If you see the voltage over here of channel 1, channel 2 and channel 3, ES1 and ES2. So ES2 waveform have a RMS voltage is 1. Similarly, channel 2 is have a RMS value is in 0.8 volt, or you can say that at 850 volt millivolt. Okay, so it is less than to this one. Okay, if you move in a right side, then see that. So displacement or distance is change as well as output voltage is change. Okay, if you come at a center point of a LVDT, then again cyronal is below, and you got a residual voltage of 22 millivolt. Okay, so this is your residual voltage. Okay, so at 10 mm you get a voltage of here 0. So now if you move armature in right side, then your distance is negative. Okay, but voltage is positive, means distance you move in a right side is negative, so that we get a curve like that. Okay, so again you move to its maximum limit. I just set it to 10. Okay, so now you see here we get a minus 10 mm output, so distance is negative, so voltage we get a minus 0.6. so now you see here we get a curve like that. Okay, and another one, if you see in previous case the es2 is higher than this one, but now the es1 is higher than es2. so if you minusing the es1 minus es2, you get a proper reading for the LVDT. So from this method we can measure a distance in mm by using LVDT. Okay, so you take a reading one by one, step by step. You can draw a waveform like that. So this is your LVDT characteristics by using LVDT trainer kit. Okay.